which is just over a petaflop. It's currently NSF's most productive center in terms of flops. We will be greatly overrun by Stampede in a matter of months, roughly an order of magnitude. And we're a major partner in Exceed, which is kind of the large ecosystem that NSF's put together with all their supercomputing centers. Within NICS, and there's the Application Acceleration Center of Excellence. I'm the director of that. The focus is on future technologies, and so I lead all of our MIC efforts at NICS. One of the key driving points behind what we're looking at is not just trying to eke the most performance we can out of all the technology, but to find a sustainable way to develop for it as well. Okay, so that's why MIC is very attractive to us. So the mission is to make sure that we prepare the nation for all of these technologies as they become available. And that involves optimizing current and future applications, developing expertise and expression of additional parallelism, because that's going to be vital on all of the upcoming architectures. And we're conducting research and education programs around this. I bring in interns. They work with our hardware. I've got 2 right now, and I'm always looking for more. And then finally, we have kind of a feedback mechanism. It's almost a co-design type effort with Intel, where we provide a whole lot of feedback to them about the applications, and they make tweaks and adjustments to the hardware and the software to improve it. So as part of that, we have a multi-year strategic engagement that we've signed with Intel that gives us access to their technology early. And in return, we give them the application testing, the performance results, and the feedback that they need. And this helps both to guide Intel and also helps us to guide the scientific community to where they need to be for scientific computing by the time these things are deployed. So to begin with, a quick technology overview. You've probably seen some of this. If you have, I apologize. I'll go through some of it pretty quickly. We start off, and this is the basic ring architecture that you'll find in the mic. You have a bunch of cores, and they all have a cache attached to them, and they're all coherent. That'll be interesting here in a second when you see some of the results. So the first development platform we got was the Knight's Ferry. It was intended predominantly to let us develop software and the software environment around the mic architecture. So the performance that you see is not at all indicative of what you should expect out of the Knight's Corner when it's deployed as a commercial product. The particular card that we had 32 cores. It was running, core speed was up to 1.2 gigahertz. I don't recall exactly what it was on our card. They wouldn't let us disclose it at the time anyway. The I/O bus on this particular version is the PCIe Gen 2 by 16 with GDDR5. Our card had 2 gigabytes of memory, and as you can see, the peak performance in single precision was 1.2 teraflops. The cool thing is, as y'all have heard, this is all Linux-based and it's IP addressable. So now we move on to Knight's Corner. And I've got the obligatory blurb up there. This is pre-production hardware. You've heard it enough times, I'm not going to repeat it. And as you can see, there are a lot fewer details that I can actually tell you, and you've seen them all. So Rook is our first SDP platform that we got from Intel that we had Knight's Ferries deployed in. We used 2 for quite a while. We've recently upgraded it to a Knight's Corner. And we've added Pawn, which is another development platform provided by Intel. It's actually got 2 Knight's Corners in it. We use it predominantly to try to do cross-card comparisons and things like that, where we're running mic to mic or running host with 2 mics, that sort of thing. Bishop is the one and only Cray CX1 you will find that has mic architecture cards in it. We put this together for a demo at Supercomputing last year. Ran it live in the booth. It's essentially 2 compute nodes, each with 1 KNF and a service node that manages it. So it's a little microcluster in a box. It's literally smaller than a filing cabinet. And it's got active noise cancellation, which makes it really nice if it's sitting in your office. And finally, this is what we're working on now predominantly. It's Beacon. It's a large, or in the scale of KNF clusters, it's a reasonably large cluster. 16 compute nodes, each with 2 KNFs. It will be upgraded to KNCs as they become available. The Beacon is funded by an NSF project that is focused on porting and optimization of various different scientific codes to the mic architecture. The project itself has roughly 8 groups attached to it. They'll be looking at everything from Enzo to Magma to Milk and Amber, and a lot of major codes. The interesting part, or perhaps the interesting part to some of y'all, might be that we will have an open call here coming up in hopefully the next month or so for participation in the project. Ideally, it would be best if you teamed with U.S. researchers to apply, but you're certainly welcome to apply. The idea is that we'll select another 12 projects probably for 2 different periods, so up to 24 additional projects to work on Beacon over the next 2 years. Okay. If you want to find out more about it or you're interested in participating, please email me. So early on, we had our own versions of MPI running with KNFs, and that was back end of last summer, actually. And we got a little creative with some NAT rules and actually ran as a cluster for supercomputing last year. This is just some details on how they set up the routing if you're interested. So on to some applications. Chemistry. The very first thing that we looked at was NWChem. It's a major application. It's used on a lot of the supercomputers in the US. Robert Harrison, who is the director of JIX, which houses NICS, was a major developer on NWChem at one point. It scales well. It's used prolifically. So what did we do with it? Well, and the other interesting thing is it's several million lines of code, both Fortran and C. Okay. So what did we do with it? We essentially just ported it to see how well it would work. We haven't done any performance studies. It's run in standalone native mode on mics. We haven't looked at offload with it yet. We're in the process. We've just recently picked this back up and gone back to it. The nice thing was it took virtually no effort to get it up and going. Okay. And as Robert Harrison's always happy to say, very little of NWChem runs anywhere other than on conventional platforms. So the mic offers a unique opportunity as far as he's concerned with the code. Initial tests all came out fine, the QA suite. I think they've gone back and rerun the full QA suite at this point, and everything was okay. I know we've gone back and tested global arrays. So everything is working fairly well from what I understand. As far as this code was concerned, some of the major points that made it simple to move to the mic were the existence of the MKL, more or less link to it and you're done. Okay. There are some vector intrinsics that were attractive. They're not used yet, but Robert wants to use them. He uses them for SSE and some other things. But in this case, he wants to move over to the AVX, to whatever we're calling all of the AVX stuff on the mic at this point. So the next application is an electronic structure application called ELK. It's essentially a Hartree-Fock type density functional theory based code. And all he did to get this going, it's Fortran 90 with OpenMP parallelization. It uses MPI, so it's a hybrid communication mode. And all he had to do was build it with the -M mic and run it natively. He didn't have to touch a line of source code. He got the correct results. And for speed ups, so he ran 2 cases, a 27 and a 64 crystal momenta case. The 27 case, because of the way the software is set up, you can't get more than a 27x speed up out of it. They came in just over 20, got, if I recall correctly, somewhere around 70% of what they were hoping to get out of it, what the maximum was limited by the software. And they moved over to a larger case to see if they could do a little bit better, and they did. This is running, once again, on the KNF, so we only had 32 cores. And they got up to about 25. So scaling's fairly reasonable for absolutely no effort. So Enzo, major cosmology application. It's run on all of the large systems. Robert Hartness, who prepared these slides, works for us part-time sometimes. And he's run some of the absolute largest simulations that have been done with this code base. I've supported him directly on machine runs on Kraken. He's moved those codes over to Jaguar and Titan. He's also run on, I believe, the early science system for Blue Waters now. So interesting case that I was involved with was this case that ran at 93,750 cores on Kraken. Okay, it was the largest cosmology simulation that's been run to date, and it took essentially a year to run this thing. In fact, he would still be running it if he had allocation. So part of that's because we only run the large capability jobs periodically every few weeks, and he was limited to about 24 hours at a time, maybe 48. So anyway, very, very large job. Now he's running on Jaguar with roughly half the size. This is an example of the sort of results that you'll see coming out of the code. Doesn't mean a whole lot to me, but apparently it's important to him. So this is the particular version of Enzo that he's using. He refers to as Enzo R. He's tweaked it so that he could get the scalability out of it. So if you just go grab Enzo as a public distribution, it's not going to scale to the full extent of Kraken and Jaguar. Roberts does. My understanding is that he eventually intends to re-release this back out into the public sphere for everyone. So interesting thing is he uses C, C++, and Fortran 90. Okay. It used a number of major libraries, Hyper, HDF5, those sorts of things. He had to get all this built. And he managed to move the entirety of this code in roughly a week by himself to the mic. And almost all of the effort went into getting the libraries compiled. One of the things that can often be the most challenging is trying to get auto-configure scripts fooled into thinking that they can actually compile because they're unaware of the mic architecture at this point. So most of the porting effort actually goes into getting configurations set up. So he's going to expand this with some additional capabilities. If you're interested, you can read about them a little bit later. I've got plenty of slides, so I'm going to keep moving. So where does it stand? He's got Enzo running on the mic architecture. It's more than 1 million lines of code. MPI, HDF5, and Hyper were all built to get that going. He prefers to run natively on the mic rather than looking at offload because of the way the code is set up. We see a lot of folks that we talk to, and even our own experience for certain codes leaning in that direction. Those that intend to try to use the nodes actually look into or are considering like a heterogeneous MPI topology rather than using offload as well. Most of them just simply don't want to give up the control of the actual communication that you do when you go with the offload model. So in addition to Enzo, he's got, and Enzo was actually straight MPI when he ran this. So I'll show you the scaling results in a minute. But in addition to that, he's got the tools running on the architecture. So these are his initial scaling results. No optimization is done at all. Straight MPI, and he ran up to, and that shouldn't say threads, that should say ranks, but it's the same thing here, because the ranks are mapped to a thread. And he got up close to, it's like 68% of ideal, running straight MPI with no threading at all across all the cores on that card. We were actually pretty surprised to see that it scaled that well straight out of the box with MPI. You may have seen some blog posting and put out by folks that imply that this model is not going to work. Well, obviously it does fairly well for some codes. Your mileage may vary though. It's certainly not what I would recommend as the ideal model, but it's a great first step to build on. And I'll talk more about the different options with the MPI later this afternoon. So he also looked at what he calls his Enzo inits code. It handles all of his pre-processing and initial conditions and sort of things like that. He ran an offload mode. You can see this is ideal here, and he's got a native build here, which does reasonably well. And then he's got an offload mode on the mic, and it doesn't do quite as well. And that's because the computational intensity is actually a little bit too low on this pre-processing routine to really benefit from that degree of parallelism to the extent necessary to compensate for the PCI bus transfers for the data. So this is primarily data processing, so the data transfers end up eating up most of his performance there. So he's got it running, and he's continuing to develop on the mic architecture. He's a very outspoken advocate. You don't have to look very far to find stuff he's said on the web. So I encourage you to do so. So let's talk about some CFD applications that we've been working with. We've got 4 different solvers. Most of these were developed to some extent in-house. The Poisson solver actually originated as a lab assignment for us a decade ago in class, actually, I believe. We've got an Euler Solver and a Boltzmann Solver that are both based basically on the algorithms that I developed for my dissertation. My intern has implemented both of those. And then we've got a Navier-Stokes algorithm that one of the other computational scientists brought to the table. It's a little bit different. So one of the key points I'll point out here is that when we move to the Boltzmann solver, Navier-Stokes, you may have 5, you may have 7, depending on exactly what you're implementing. You'll have order 10 state variables per grid point. Well, with the Boltzmann solver, it's not uncommon for us to have 100,000 per grid point. So it was a very ideal case for parallelizing for the mic, and you'll see that in a minute. So to start with, we're going to go with a Poisson solver. I don't want to go through all the details, but it's the standard Poisson equation. It's simply solved with it's linearized and solved with symmetric Gauss-Seidel with SSOR. Nothing special going on there. Solutions. He ran this in offload mode and native mode to try to get a comparison between the two. In this case, he notes that offload mode is like the GPUs, and it is. He used implicit offloads, which is one particular type of offload that you can use. Essentially, he flagged the functions that he wanted to as attribute mic, and then they were implicitly moved to the migrated form when he wanted to run them. And then native, he just ran directly on the coprocessor. So let's look at the results. This has both the native and the offload on it, so it's a little bit busy. I apologize for that. This red line right here is Amdahl's law, okay, with a 99% parallel fraction. I think that should probably be 96% if I recall correctly. But you see the offload model runs pretty well, runs pretty close to what you expect to get compared to Amdahl's law. But the natives really don't. There's a reason for that, and the key is, as I said a minute ago, the serial fraction is almost 5% on this code. And that hurts on the mic because the cores on a per core basis are considerably slower than the Xeons. So when you want to move to mic, it's imperative that you get as much parallelism out of it as you can, get your parallel fraction up as high as possible. I'll show you the results of that in just a minute with the Boltzmann code. So this is the offload, and these were on K and F, by the way, Knight's Ferry. I just stuck in our K and C results this morning for your benefit. You can see we get pretty good performance once again with the offload mode. I can't tell you how many cores that our card has, but it's more than 50. Okay? But you can see some interesting behavior here. We're superlinear, right? And we talked about the cache earlier being attached to cores and things like that. And so that's what explains this superlinear effect here, is the way the cache is actually set up on the chip. We move on to the native mode once again. And here we actually have the 96% plotted, and you see that for the largest case, he's getting pretty much the best that he can hope to get out of it because of Amdahl's law. He just simply is not parallel enough. So one thing I can say is that the K and C cores are faster than the K and F cores, right? Or the performance on the K and C core is better than the performance on the K and F core. So, yes. So we do see some improvement on that front. And like I said, once again, with the native, he's getting about everything he can out of this given the parallel fraction on this code. Basically, the standard sort of notations that you'd expect. Larger problems are better, that sort of thing. We're moving to look into actually mixing the offload and native in some interesting ways to see how we can make best use of the topology depending on the particular problem and code that we're working with. So let's talk about the Navier-Stokes solver. This is an elliptic solver for incompressible Navier-Stokes. It's finite volume based. It runs on, I believe, a curvilinear mesh. And it's built for distributed computing across a high latency network. So it's a level set method, and it uses an Aitken-Schwartz domain decomposition. We don't need to talk about equations, but this is how he formulated his incompressible Navier-Stokes, the numerical formulation for what he's doing. And great, we have animations. So you solve each domain, then you go in and you update the interface and you repeat. It's a standard sort of numerical algorithm. It's converging, it's not converging rapidly, so they apply the Aitken acceleration to it. Here's the algorithm for it. And here are the results. Strong scaling on the Navier-Stokes 2D. He's getting, I think it was about 17 out of 20 up there. And then the weak scaling, you see he's better than 75% at 20 cores. I'm not real sure why he didn't choose to run all the way up to more cores, but this is what he ran, this is what I had. So these were the 2D results on KNF. Here are the 3D. It falls off a little bit. It's not quite as efficient. The particular algorithm he's using here is somewhat simplified for a very specific set of flow problems. And so it minimizes, to some extent, the computational intensity compared to a more general method. And that's one of the reasons why it just simply doesn't have enough work to scale as effectively as some of the other algorithms might have. So the speed up on the Navier-Stokes, here you see Amdahl's for 95%, and you can see he's below that. Okay. So once again, the parallel fraction is really not as high as we'd like to see it for Mike, but we're still getting good performance. So that's one thing to note. I mean, if you look at the scaling, and I'll show you here in a minute on the Boltzmann code, you get very solid scaling across the cores. So whatever performance you can pull on one core, you can pretty much expect to maintain it fairly well across all of the cores on the card. Okay. Now, whether that's going to give you 80 or 90% of peak, I really seriously doubt. Very few algorithms can pull off 80% of peak on anything, right? And so if you're running at 20% of peak on the Xeon, you're probably going to see something similar on the mic until you've done some work on the algorithm. Okay? The difference is the penalty for not doing that work and running on the mic is larger because the mic has more resources. Okay? If you're going to go to the architecture, spend the time. It doesn't take a lot of time. I mean, I'll show you in a minute. In a matter of a week or two with one intern kind of working off and on with an engineer, we saw some substantial improvements in code. And so I encourage you to spend a little bit of effort when you move to the architecture, and you'll see the payoffs both on the mic and on the Xeons themselves. So now let's go to K and C results. Well, the K and C results are not quite as nice. Why? Well, because nothing changed at all in the problem except the cores got faster. So of course the scaling went down a little bit, right? Same thing on the weak scaling here. Same thing for the 3D. And once again, we're still well below the 95% mark on Amdahl's law. Nothing surprising there. It's just simply a case that has not been optimized to take full advantage of the architecture. So let's talk about the Euler Solver. I'll give you a little bit more idea about how the algorithm works in a minute when I'm talking about the Boltzmann Solver. But this uses the same basic algorithm. We ran initially a side shock just to make sure we had things working correctly and to see how it worked out. And on the 32-core card, we got up to, I believe it was 99% of a 32x speed up. Not too bad. So this is probably one of our better results for just an initial out-of-the-box run. And let's look at the Boltzmann Solver now. So to give you an idea of how this solver works, it's a point-iterative Newton, in this case, Jacobi scheme. It employs dual numbers to actually calculate the Jacobian values on the fly. So essentially all it does is iterate over the residual vector and do updates continuously. So it vectorizes very well, and it's got a lot of compute intensity. So currently this particular code is implemented in single node on OpenMP. It was optimized with my intern by Rob van der Vengart at Intel. As I said, it was roughly a couple of weeks worth of effort off and on between Rob and Ryan. I'm going to establish a baseline here, and it's for the point of discussing a slide here in the future. This baseline is a particular version of the code that we had that had most of the optimizations in place, except we had problems with one loop that just would not vectorize. Okay, and we knew what the problem was. Rob had discovered the issue and told us about it, and it had to do with the way that we were using template functions, and we were constructing stack variables with template functions, and the compiler just couldn't see through what was going on. And one thing to note is that this particular code has more exposed concurrency than the available number of threads, so we're not limiting the speed up at all by the software. It's just the hardware that's going to be limiting it, pretty much. That or poorly written software may limit it, but the case itself is not limiting it. And finally, the performance results that I'm about to present for the optimization portion were obtained with 2 OpenMP threads per core. And they're presented relative to this baseline solver that I was discussing. So we were talking about parallel fractions. I want to show you why this code works as well as it does. We've got a parallel fraction of less than 0.001. Okay, it's a serial fraction of less than that. We've got a parallel fraction over 0.999. It's almost completely parallel, and so it moves to the mic very well. So let's look at a couple of cases. This is a Coet flow in which this wall over here impulsively starts moving. We generate correct results, and these are the speedups we got out of the initial code. In the dotted line, this is the baseline code that I discussed, and then after the optimizations were complete, you can see we got on up to the 32x that we were hoping to get out of the card. So what sort of optimizations were done? I'm going to walk through a list of them, and then I'll show you a chart that kind of compares some of them, and I'll comment on the couple that were the most important. The first thing was the loop vectorization. We fixed that loop, and ran it again. We converted the class into a structure, and we convinced the compiler to actually vectorize it. Okay, sometimes it's a little difficult, but in this case it wasn't. Then we looked at data access, aligning the data and linearizing it, making sure that it was available to load as effectively as possible. We reduced the number of individual parallel sections in the OpenMP code to cut out some of the parallel overhead there. We removed the dependency in one of the computational loops, essentially by setting up private variables to sum into, and then computing the sum after the loop. And that allowed it to vectorize more efficiently than it had been on that loop. Then we looked at using medium precision for some of the math function calls, because we didn't need much more than that. And finally, we looked at using single precision constants and intrinsics. In this case, the constants are essentially free. We don't use constants that have more significant digits than we can represent in single precision anyway. And then finally, we played around with some of the compiler hints to try to convince it to be more aggressive in its vectorization. So what did we get? Well, the baseline is here at 1, and just by fixing the one loop that was not actually vectorizing, we got about a 3.5x speed up. Okay, so that's very important. When you get ready to work on your codes, make sure that all of your loops are vectorizing. That's the first thing you should be concerned about. Okay. We applied all those other minor changes, and then ultimately we got to the single precision for constants. And this was a little surprising. We picked up another 2x roughly just by using single precision on our constants. Okay, and as I said, that's pretty much free. We didn't really pay a price for that at all. And finally, when we were playing around with the compiler hints, we didn't really see too much difference. By that point, we had more or less stretched the vectorization as far as the auto vectorization would go. Optimization results. This is the code that the end result, the final code, and this is the scalability for it. We ran it on the same case we had been using, and we ran on a card with greater than 50 cores, and we got a 51.1x speed up out of it, running at 100 threads. Moral of the story, use the vector reports even if you think your code is set up correctly, just so that you can know for certain what the compiler has actually done. Yes. So back to the results. Our initial results got this 51.1x speed up on the card. Well, it turns out we weren't using all the memory available to us, so we doubled it, and we got a 73.5x speed up off this card, which was actually very good. There's a little bit of headroom left to grow. We just couldn't double the mesh again. So it's possible that we might even be able to stretch that a little bit farther. We're going to go back and try anyway. But, and once again, just as a reminder, the reason that this scales as well as it does is because the parallel fraction is almost completely 1. And so that's, this is kind of pushing the extent of what you should really see or expect to see out of some applications. Most applications are not going to be quite that parallel. And so we saw examples earlier with a 95%. But the point was we got pretty much Amdahl's law out of the card with very little effort, very little in terms of optimization. So in summary, we've got this Boltzmann BGK solver we've been working on, and it's ported and optimized and running real well. And we're getting great, strong scaling results. If you want to get the maximum performance out of the card, the vector unit is wide, and you've got to use it. Okay? That said, you can get great performance out of just scaling across the number of cores. Right? You'll be able to look at what relative performance is per core on a Xeon at some point in the upcoming months or something like that. And then you can look at how many cores you've got on the mic, and you can see whether or not that's going to benefit you in terms of that ratio. We're finding that in most codes we look at, it does, even if they don't have a 99% parallel fraction. A lot of codes just benefit from having the extra cores. Okay? And then finally, the single precision point, which was, as I said, a surprise to me last week, 2 weeks ago actually now. But that's essentially free. I mean, all you have to do is tag your constants in single precision, and you're getting performance out of it. From here, we're going to start looking at the offload versus the native model, do some comparisons, and we're moving to an MPI plus OpenMP so that we can actually run across the cluster and get some full scaling. We expect to have all of this done for supercomputing. And we'll be working across the multiple cards and then across multiple compute nodes. So anyway, contact list if you need to talk to any of us about this. And so the interesting thing here, and like I said, that's supposed to be 96, not 99. There's a typo in that. It's because there's a large enough serial fraction to actually benefit from having direct access to the Sandy bridges. Okay. When you run natively, that serial fraction is running at the smaller performance of the mic core. So, depending on your application and how it breaks down, you can adjust how you map it to the Xeons versus the Xeon Phis. Okay? And that's one of the nicest things about this architecture, at least from our point of view, is the flexibility you have with the programming models and the methods that you can employ. It gives you the freedom you need to express your algorithm reasonably effectively, reasonably easily, relative to the actual architecture. And so our expectation is that most people will be able to achieve a pretty reasonable usage of the card without having to totally refactor a code.
So essentially, what this offload mode means is that you are decreasing the actual serial part by running on the serial.
Well, the serial part is running more rapidly on the Xeons, and so it has less impact on the overall performance. You can accomplish the same thing without using offload, and I'll discuss that this afternoon in the API talk. You can use, in essence, I'll refer to it as a reverse offload, which is not technically supported by Intel through directives, but you can implement it with MPI. I mean, you can put an MPI rank on each socket if you want to of the host, and then on each card, right? And you can partition your communicators, and you can control what you're actually doing there so that you can balance the load on those and send the serial parts off, right? And so there's, like I said, there's a whole lot of flexibility here. You're not locked into a single model. You know, Intel's not telling you, we made this card, you must write this way to make it work, right? Instead, they're giving you a variety of tools and asking you what else they need to give you so that you can make it work, right? And the overall impact is pretty significant. As I said, almost everything we've done has been very small amounts of effort. I have a very small team of people, and most of them, I have 2 interns that I have full-time, and I have 1 other person that I have part-time, okay? And we're working across all of these codes, and I mean, we don't have the time to go in and optimize these directly. And that's important to us because at the Supercomputing Center, I was a computational scientist before I took over ACE. I was supporting a half dozen projects at least, and we have 4,000 users, right? Computational scientists at the center can't sit down and optimize every code. We can teach the users best practices and hope that that helps, and then we can help on the hardest parts. And the nice thing here is that the mic gives us the flexibility we need to be able to attack those problems relatively straightforward manner. In the mic, you have a bunch of cores, and they all have a cache attached to them, and they're all coherent. That'll be interesting here in a second when you see some of the results. So the first development platform we got was the Knight's Ferry. It was intended predominantly to let us develop software and the software environment around the mic architecture. So the performance that you see is not at all indicative of what you should expect out of the Knight's Corner when it's deployed as a commercial product. The particular card that we had 32 cores. It was running, core speed was up to 1.2 gigahertz. I don't recall exactly what it was on our card. They wouldn't let us disclose it at the time anyway. The I/O bus on this particular version is the PCIe Gen 2 by 16 with GDDR5. Our card had 2 gigabytes of memory, and as you can see, the peak performance in single precision was 1.2 teraflops. The cool thing is, as y'all have heard, this is all Linux-based and it's IP addressable. So now, because that's going to be vital on all of the upcoming architectures. And we're conducting research and education programs around this. I bring in interns. They work with our hardware. I've got 2 right now, and I'm always looking for more. And then finally, we have kind of a feedback mechanism. It's almost a co-design type effort with Intel, where we provide a whole lot of feedback to them about the applications, and they make tweaks and adjustments to the hardware and the software to improve it. So as part of that, we have a multi-year strategic engagement that we've signed with Intel that gives us access to their technology early. And in return, we give them the application testing, the performance results, and the feedback that they need. And this helps both to guide Intel and also helps us to guide the scientific community to where they need to be for scientific computing by the time these things are deployed. So to begin with, a quick technology overview. You've probably seen some of this. If you have, I apologize. I'll go through some of it pretty quickly. We start off, and this is the basic ring architecture that you'll find. So it's a little microcluster in a box. It's literally smaller than a filing cabinet. And it's got active noise cancellation, which makes it really nice if it's sitting in your office. And finally, this is what we're working on now predominantly. It's Beacon. It's a large, or in the scale of KNF clusters, it's a reasonably large cluster. 16 compute nodes, each with 2 KNFs. It will be upgraded to KNCs as they become available. The Beacon is funded by an NSF project that is focused on porting and optimization of various different scientific codes to the mic architecture. The project itself has roughly 8 groups attached to it. They'll be looking at everything from Enzo to Magma to Milk and Amber, and a lot of major codes. The interesting part, or perhaps the interesting part to some of y'all, might be that we will have an open call here coming up in hopefully the next month or so for participation. We move on to Knight's Corner, and I've got the obligatory blurb up there. This is pre-production hardware. You've heard it enough times, I'm not going to repeat it. And as you can see, there are a lot fewer details that I can actually tell you, and you've seen them all. So Brook is our first SDP platform that we got from Intel that we had Knight's Ferries deployed in. We used 2 for quite a while. We've recently upgraded it to a Knight's Corner. And we've added Pawn, which is another development platform provided by Intel. It's actually got 2 Knight's Corners in it. We use it predominantly to try to do cross-card comparisons and things like that, where we're running mic to mic or running host with 2 mics, that sort of thing. Bishop is the one and only PRACE EX1 you will find that has mic architecture cards in it. We put this together for a demo at Supercomputing last year, ran it live in the booth. It's essentially 2 compute nodes, each with 1 KNF and a service node that manages it, which is just over a petaflop. It's currently NSF's most productive center in terms of flops. We will be greatly overrun by Stampede in a matter of months, roughly an order of magnitude. And we're a major partner in Exceed, which is kind of the large ecosystem that NSF's put together with all their supercomputing centers. Within NICS, and there's the Application Acceleration Center of Excellence. I'm the director of that. The focus is on future technologies, and so I lead all of our mic efforts at NICS. One of the key driving points behind what we're looking at is not just trying to eke the most performance we can out of all the technology, but to find a sustainable way to develop for it as well. Okay, so that's why mic is very attractive to us. So the mission is to make sure that we prepare the nation for all of these technologies as they become available. And that involves optimizing current and future applications, developing expertise and expression of additional parallel